much. Yeah, so today I will try to talk about different concepts, let's say, or like how can we look on both humans and deep networks from information perspective. So first, I want to say thank you to some of my collaborators. They did all the work, basically. So we will start with saying maybe like the abstract, like the summary of this talk, or like the bottom line, is that communication is a fundamental an act of compression. And we want to understand exactly, I will talk exactly on this on this gap, like how human compress versus how models or AI compress their representations. I will talk about what is exactly means the compression and humans and AI and all these things in a minute. Okay. Um, and in general, my vision, or like my research vision, is to first to understand, or like to get some insights from representations um, about humans and models, and I'm using information theory tools. And then in the next step, we also try to improve these models based on these insights. Today, I will only talk about the first part, which we are trying to understand these models. So if we're talking about information theory, I think we need to start with Claude Shannon, the father of information theory, and maybe also the father of machine learning. That said that the best approach is to look, or like to try to solve a problem by looking on this problem from many different directions. And this is exactly what I'm trying to do personally, and to look on a problem from different directions. So yeah, you can look on compression from different directions and different point of views. And as I said, in this talk, I want to talk about compression and how human and AI compress information and how they create their representations. Okay. So I will try to talk about 4 different studies. I'm not sure we will have time for all of them, but at least for the first ones. So I will start with trying to compare LLM versus humans in how they represent categories and how they manage the trade-off between compression and semantic representation. Then I will talk about debate and how can we compress debates, or like what are the strategies that we can use in order to compress debate documents in order to create the perfect debaters and how it's related to compression. And at the end, we will talk about chess and how humans, how the representations of humans and the actions of humans are different from models. So, by the way, if you have questions, you can ask, let me know. You can do it also like during the talk, and I'm hopefully we will have time also at the end. Okay, good. So what is a good representation? This question is very fundamental, right? It's a very fundamental question, and a lot of people try to answer this question from different perspectives. And as I said, today, or like in general, I'm trying to answer it from information theory perspective. So what is a representation from information theoretic perspective, a good representation is a representation that preserves relevant information while at the same time compress this representation. Okay, so we have a trade-off. I will talk again, I will try to formulate a bit what is information, what is compression, and all these things, but intuitively, we want a representation that we will compress the irrelevant information, that will compress all the things that are irrelevant, while at the same time, we'll keep the things that are relevant and we want them. Okay, it's very intuitive. Now, let's try to formalize it a bit. So imagine that you have X, your data, your observed data, right, your input, and you have some labels, Y, and you want to ask the question, you have a model now that you want to learn a representation of this model, Z. Now you want to ask the question, what is the optimal representation of this model? Now, apparently, Tali Tishby 25 years ago answered this question. And the answer is that you want to maximize a trade-off between the information that you keep on the input and the information that you keep on the labels. Okay, so here the I is the mutual information, like how many bits I have, how many bits one random variable tells me about the other random variable. Okay, so I want to compress IXV, the information about the input, while at the same time I want to preserve the information about the labels. I want to increase IZY. Okay, so IZY is the prediction ability, how well I can predict the labels, and IXC is the compression or the capacity of my model. Okay, and beta is a trade-off parameter, or if you want the Lagrangian a parameter that control this trade-off. So if I'm taking beta to infinity, okay, I will keep all the information and I will not compress anything. If I will take beta to 0, I will compress I can compress everything, but my prediction ability will be very bad. Okay, I will not predict the labels. Questions? Okay. Great. So why the prediction or the information with the label is good is quite obvious, right? Like you want to predict, you want a better prediction. So this is very easy to, I think it's much easier to understand, but why we actually want compression? Why we care about compression? So there are different answers to this question, but we can show that the information that I have with my input actually bounded the generalization gap. So what is the generalization gap? The generalization gap is the difference between the training error and the testing error. Okay, so remember, I'm training on some data, and now I want to test it on other data. I want to see how much I can generalize to other input, to other data points, and this gap is the generalization gap, and I want to make it smaller as possible. Okay, so now if I compress the input, I compress the information, and because I compress the information, this generalization gap become smaller and smaller. Okay, so more compressed representation will bring me to better generalization. Okay, good. So remember this trade-off: compress more, you will have better generalization, but you can hurt your prediction ability. So compression, intuitively, you can think a good example is that you have, for example, you want to classify between cats and dogs, okay? And you have the same picture of dogs with just different backgrounds, okay? So think that now you want to learn a classifier. So if you have all the information, if you keep all the information in the image, you need all the different backgrounds basically in order to classify everything correctly, right? So you need a lot of examples. Now think that you will compress the background. You just ignore the background. So basically you need only one image, and now every new image you can compress the background and you will know how to classify, right? So this is again it's very a simple case, but this is intuitively why compression can bring to good generalization. If you know to separate between relevant information and irrelevant information. Okay. So yeah, so you can think about also in tags, right? Like if you have raw data and then you compress it more, you have some patterns and you have rules and you have some principles, and you want basically to learn these principles, these high-level principles, in order to get better to understand what does it mean and what are important part in your data. Now, there are different ways people try to quantify it and define it in different ways. Maximum, minimum description length, Kolmogorov complexity, a lot of different terms. But in principle, it's the same thing, but with different point of views. Okay. Now you can look also on communication as type of compression, that you basically try to pass your input from the source to some destination through a channel, and you need to compress your input through this channel, but at the same time to get good prediction in the output. Okay. So yeah, and we are using these different complexity levels all the time, right? Like when we think and we have some thoughts and we want to derive the words, or like we have some research and we want to get some abstract of this research, some high level abstract, or and we have it all the time, and in our work we are trying to quantify it. Okay. So let's start with the first question. Okay, how humans and LLMs trade compression and meanings. Okay, and more concrete question is, do LLM develop human-like conceptual representations? Okay, so let's start with humans. Humans, they have we have, right, we have both. We can say, okay, so we have kind of compression because we say that robin or blue jay are types of birds, right? We have this meaning of concepts, okay, that we know. We are taking different different words, or like different animals, or different like types of something, and we can say we have some abstraction, and we can say all these types are something, all these birds are all these terms are birds, for example. Okay. There are different let's say studies that are trying to explore and why we have it and what are exactly our concepts and how we are generate these concepts. I will not get into these things. But yeah, but we have also we preserve the meaning of these concepts. Okay, so like robin is a typical bird, or penguin is a atypical bird. Like we have these typicality thing that like we know we have some concepts or clusters, and we have some typicality, and we know to understand like inside each concept what are typical terms for or like objects for this concept, and what are atypical objects. Okay, we have very rich semantic structure that we can use, or after we build it, we can use it. Okay, and again, we have here the same trade-off, and this is important. We have, from one hand, we compress some of these things, right? All the different types of birds are birds, and from the other hand, we preserve some semantic fidelity, right? Like we know how to extract the relevant features. Okay, and in our research, we asked 3 questions. So the first one is very simple. Do LLM has the same clusters as human, is human basically, and if the categories are match between humans and LLMs. The second question that we ask is, do LLM capture the same typicality within categories? Like if the structure of the category is the same, okay? And the third one is how LLM versus humans, how they compress the information, or like what are the trade-offs in LLMs and humans between keeping the relevant information and keep the information that you need in order to understand, and to compress and to remove all the redundancy. Okay, what we have done, we took, in order to test it, we used 3 human baselines, 3 studies, cognitive studies that basically they ask people different questions, but at the end they asked how much banana is close to fruits, for example. Okay, for different categories. So we have more than 1,000 items that came from humans. Okay, and this is important. Like these studies ask humans the relationship between the categories, and we took different LLMs, a lot of models, different types of models, encoder only, decoder only, different sizes, and we try to compare. Okay. In order to compare, we use the information button that I explained before. So here in this case, the information bottleneck is exactly this trade-off between the complexity. Okay, so see here is the category. So we want to remove the complexity, right? We want to remove the redundant information that we have inside each category. And at the same time, we want to keep the relevant details in order to make a good prediction, or in this case is the distortion, or how can we reconstruct the original meaning from the clustering. Okay, and in general, as we saw before in the information bottleneck, we lower our loss, or like as lower L, we are more optimal, and we can preserve more information, more relevant information, and to remove the irrelevant information. Okay, great. So the first question, we want to just to remind you, we want to ask, do LLM clusters the same categories as humans? And in order to do it, we extract the embeddings from LLM. We ask basically the model the same questions as we ask people. We looked on these embeddings, okay, and we cluster these embeddings with k-means, and then we looked on the clusters from humans, and we compare it to some random baseline. So we measure the information that the clusters of humans and the clusters and the embedding clusters of LLMs. Okay, and we looked on different types of information, metrics. If you know, like there are a lot of different types of metrics and ways to measure information. I will not get into it. If you're interested, you can ask me later. And I think that there are pros and cons, and like maybe Oscar will also talk about information metrics a bit after it, but there is no one way that we can say, okay, this is the best way to measure information, and it really depends on your assumptions and things like that. But we tried several of them. Okay, so what we see here, so y-axis is basically the information, and the x-axis is the model size, and basically 0 is like random clustering. So we want to, if it's above 0, we can say that like that that humans, that the clustering of LLMs are aligned with humans more than random clustering. Okay, and so first of all, as you can see, all the clusters are more than are bigger than 0, and the surprise thing here is that BERT model, encoder-only models are they store much more information compared to other models. So, and this is, if you think about it, it's not surprise, because encoder-only models are, they have like a general representation, right? They can look on the whole, basically on the whole input, and they don't squeeze out or compress only for the next token. So this is how you build it, and we can see it here. They store much more information, or they are much more aligned with human clustering. Okay. Okay, great. Okay, good. Now now the next question, we wanted to look on if LLM captured the prototype of the categories. Okay, so like Rubin is a typicality prototype of bird versus penguin that is not, basically. So in order to do it, like we looked on the cosine similarity, okay, between the different between the different I don't know, like the different, for example, here the different birds, right? The different low level in the hierarchy. Okay, So what we see here, okay? So here, so y-axis is the correlation, okay, for different models of the constant similarity. So if it's typical or not. And in general, we see the correlation here are quite weak and not significant. So it means, as I said, it means that the LLM basically they don't capture the same typicality that humans have. That they don't understand that Rubin is like more similar to a bird than penguin. Okay, so their internal structure is different from humans. Like they basically treat all the birds the same without like the meaning of, oh, this is more close to a bird, so Rubin is more close to a bird than penguin. Okay. um so I think it's interesting because it says something about, like, okay, we have the general structure, we have the clusters that humans are quite aligned with LLMs, but inside the clusters, we see that we don't have any structure for LLMs. They don't say like, okay, I have very specific structure inside it, and then maybe like it helps in some other way, or like for other tasks, but we just have very uniform clusters. Okay, and the third question that we asked, and in my at least in my perspective, is the most interesting one, um, is how efficient are the representations are. And when we compare LLMs to humans, and this balance that we talked before between complexity and distortion, okay, how um, how the representations behave when we compare humans to LLMs. Okay, so basically what we have done, we looked on human categories, we looked on LLMs, the clusters of LLMs, and we look for different cases. So we clustered the representations with different number of clusters. Okay, and we calculate the entropy for each cluster. Okay. So as I said, we have here two terms. One is the complexity of the representations versus a distortion, the intra-cluster variance. Okay, like how well I can reconstruct the input. And also, again, if we have better efficiency, it means that we have lower values. Okay. So just to say before we see the results, okay, let's try to see what is happening in general in deep networks. Okay, how deep networks store information, or like what are the dynamics in deep networks. So this is a paper, our paper from 2018, opening the black box, that we found two different phases. Okay, so here x-axis is the information that we store about the input, and y-axis is the information that we store about the labels. Okay, remember, we want a better trade-off is to be in the left upper side. Okay, and to be more efficient and to store more information about the labels. And we found two distinct phases. Okay, so each color here is a different a time point. Okay, so at the beginning we see that we measure. Sorry, I will explain better. We measure the information in each one of the layers. Okay, we measure the information that we have about the input and the information that we have about the output. okay, for each one of the layers. So in this network, we have 6 layers, okay? And the final layer, so if you can see, so at the beginning, the bottom left point is the final layer at the beginning of the random initialized network. And now we train the network, and we train it without any specific regularizer, okay? And we measure for each step and for each epoch, we measured the information for all the layers. So each point here is a layer at different time. And what we can see here is that we have 2 distinctive phases during the training. One, the first one, is a rapid increase in the information with the labels, okay? So you can see that at the beginning, all the layers basically improve their accuracy or their performance. And this is very fast. And at the end, the second phase, and this is most of the time spent on this second phase, we see a very strong compression. Basically, all the layers compress the representation with the input, and at the same time, they increase their representation with the information with the labels. Okay, so we see very strong compression during the training without any explicit regularizer. Okay, and we also have like a theoretical works that show that during the training during SGD we probably will see this compression most of the time. Okay, so we know that LLMs and neural networks in general that train with SGD will compress their representation. Okay, will be very efficient. Now let's try to compare it to humans. Okay, so here we can see, so x-axis is the number of clusters, like the information basically that we have in the representation, and y-axis is exactly this trade-off. Okay, and again, remember, lower is better in this graph, and each color is a different model, and you can see here that LLMs are much better or more efficient than humans for almost like all the values of clusters, and we saw it for different data sets, different model sizes, and at the end we see that LLMs are much more efficient than humans. Okay, they preserve only the information that they need, basically. And now, so why is why it's important, and what we can say about it. So, like in general, okay, we see that humans or humans categories, okay, are much more diverse inside each category or inside each cluster compared to LLM clusters. Okay, so for the similar level of abstraction, each cluster of LLM is less diverse than human cluster. Okay. So yeah, so the bottom line is that LLM optimize for kind of statistical efficiency versus humans that optimize that their optimization end up with much more richness representation. Okay. Okay, and what we can do, what we can do with that, and why it's, can we take it and actually to train LLMs to be more or like less efficient and more aligned with humans? It's a good question that we are trying to work on. Okay, so to conclude this research, LLMs, if we look on the categories in general, LLMs has the same categories as humans. The categories are aligned and contain a lot of information, shared information. However, when we looked on the structure of these categories, okay, then we have a differences between LLM and humans, and basically LLM don't have this structure, or their structure is not aligned with humans. And when you look on the efficiency of the representations and the clustering, then we see that LLMs are much more compressed, and they contain, the representation is much more compressed, versus human that has much more rich semantic representations. Okay, nice. Yeah. Okay, so I don't have a lot of time, so I will go briefly about one more cool project. I think it's cool. Um, about debates. Okay, and like how can we look on debate as compression, or like how to look on debate as a way to compress the data, and what we can say about the difference between humans and models. So there are two papers that we have about it. Let's start with the first one. So I got a year and a half ago a very unexpected email from high schooler debaters that say that they have data, um, and they want to train models on debate cards. Okay, so if you don't know, debates are quite big thing in the US, and there are a lot of people that that compete with in these debate competitions, um, and they talk with them, and I try to say to them that like, look, like if you for modern LLMs training, you need a lot of data, basically. And how much data you already have? And then they said, we have 3.5 million documents. Okay, yeah, so I said, sure, why not? And apparently, yeah, they collected a lot of data for a long time from different schools, and it was great. Okay, so why it's so interesting? Why debates are so interesting? Um, because at the end you have a topic, okay, some topic, and you basically need to compress all the paper that you read and all the documents that you read about this topic to very compressed representations, okay? And it has very specific structure that you need to compress to, and you need to understand how to do it very efficiently, really fast. Okay. So there is also like you need to do it fast because you talk really fast, and the as I said, the most interesting thing here is that you basically you have a very high quality summarization or compressed information of human knowledge, okay, in these debate cards. So this is why I thought it can be very interesting to learn these debate cards. Okay, this is how a real debate card looks like. Okay, you have different categories. I will not get into it. There are also like a lot of different forms and different versions for debate competitions. But you have like you have the title of the subject, and you have evidence um, about it and about the debates and things like that. Okay, great. And as I said, this is a huge compression. Like you basically take all the data and all like a lot of documents and compress them to very specific high quality information. Um, Right. So as I said, they are very why debate cards are so interesting because they are the perfect training data. Like they created by a lot of experts, and they already they worked on them for a long time, and we know that they're really good because they used as debate cards in competitions already, right? Um, so what we have done, we build a data set. We collect, parse, clean, annotate, and validate this data set. You can use this data set. It's on Hugging Face. Okay. And here are some numbers for this data. Um, yeah, I will not get into it because we don't have time. Um, but yeah, we learn these, we use the LLMs in order um, to train these data, to train on this data. And we found that, first of all, as we give the LLM, the model, more data, more debate data, the compression, it becomes better and better. And also, and this was quite surprising, it was better on other topics and other data sets. Okay, and this is again related to generalization, right? We talked about it, that compression brings you to better generalization. So it's not so surprising that if the model understands, learns how to compress their data and compress their ideas, it can be better in different domains. Okay. So yeah, so as you can see, the debate is very nice way to look on or to test compression. Okay. Now, um, uh, again, we did a lot of different things here, but I want to have one more study or like next step. Okay, after we train on this data. Um, so the next thing that we have done after we look on we trained models in order to be much better compressors, if you want, or like to compress their data, we try to build the perfect debaters. Okay. um how can we actually win a debate? Okay, how can we actually make a perfect debater that will win in a debate, that will compress all the information to very concrete summarization and will be better than humans? Okay. And this is what we have done, the autonomous debater. um, Okay, so the requirements are like we have access to a lot of documents, all the documents. We need to find the relevant evidence really fast, and we need to build these arguments and to make a strategy in real time. Okay, we have two main challenges. One is the real-time data access, and the other one is the single agent bottleneck. Basically, that you have a lot of information, but you need to, like a single agent can't handle all this information. So for the real-time pipeline, we basically we used a lot of engineering tricks in order to access the data and to get it really fast. I will not get into all these tricks. And in order to make the agent more capable, we used a multi-agent approach. So we have different agents and they communicate between them, and we restrict their information, restrict only the relevant information for each agent. Um, And that's it. Basically, we have some pipeline how we actually did it, but I don't have time, so you can read the paper. Um, and as I said, we try to manage the information between the different agents in order to maximize the individual information and reduce the redundancy information between the agents. Um, did we success? We tested. We tested. We gave the results to the debate, the arguments to debate coaches. Okay, we asked them to rate it with different metrics. So the results, our debate agent. Um, was much better than humans. It got much better results in all the different metrics. So yeah, we also try to look on different rounds, how it adapt the strategy if you have several rounds. Okay, how it get the I don't know the counter debate from other people and how it adjusts it and adjust the strategy. And also here we got better results than human. We did also some evaluation study, how much each component basically helps. So multi-agent versus single agent, and to summarize, we different that we were better in different quality metrics.